in an introductory class in electricity and magnetism. And what I'm going to do in this lecture is a whole bunch of math. I'm going to start doing physics, and then it'll turn into a math problem, and then we'll turn it back into a physics answer. So what we're going to solve is we're going to determine the electric field of a thin, uniformly charged ring. Uh, so the so this is going to be a problem. I'll draw a picture and sort of describe what I'm talking about in a second. Um, so there is a single learning outcome, but it's actually kind of got a lot to it. So in this lecture, we're going to get a result. So you have to understand how to use the result. Also, like, when is the result applicable to your problem? Also, you want to learn how to um, maybe understand the steps of the solution well enough such that if you had a problem that the result didn't answer, then it may be that you can get yourself an answer by making an adjustment to one of the steps in the process. And you'll be able to then use the solution in some sense, like the entirety of the solution, that is, the steps of the solution, to solve related problems. So the way this is, so the way that I'm going to do this for you, essentially this entire lecture is devoted to solving only one problem, and it's, and you'll see the problem that I'm going to solve. So we'll start by setting up the problem, and then sort of conceptually exploring the problem. And what I mean by that is we're going to first start with a test charge, and we're going to wander around our charge distribution with the test charge and sort of check the electric field, the direction, as well as the strength. And we're going to do this conceptually. That is, we're not going to do much any math, really. Then we're going to imagine which variables are going to show up in the result, that is the answer. And we're going to make judgment calls, that is physics decisions, on roughly how the answer has got to depend on the variables. And then we're going to imagine drawing the ring of charge in a convenient coordinate system. In particular, the coordinate system that I'm going to use, which you might have to review. So I'm going to put review cylindrical coordinates. So cylindrical coordinates are, so I'll show you what I mean in just a second. And then, so this actually is our problem. So the problem is determine the net electric field along the axis of symmetry of a ring of charge where the charge is uniformly distributed on this ring. Hopefully, during our answer or the solution steps, you're going to see that there are very generic steps of the solution. That is, you'll be able to see that they also showed up in the previous lecture, lecture 7. In the previous lecture, there were some steps that showed up, and those steps are always going to show up in any sort of problem of determining the electric field around a charge distribution. And the idea is recognizing these generic steps is sort of the beginning of you being able to determine the electric field anywhere of any charge distribution. It's just that complicated charge distributions lead to complicated mathematics, and sometimes the integrals that you get, you have to do them on a computer because there aren't any closed form answers to them. So you get approximate answers. But approximate answers, quite honestly, are good answers too. They're useful, especially for engineers. Okay. So a uniformly charged ring is what we're trying to get the electric field for, and I said we would start off by describing the problem and the problem sort of setup, and also to explore the problem conceptually. And so here's how I'm going to do that. So first, I'm going to draw a picture, so a diagram of our charge distribution. So it's a uniformly charged ring. So I could draw the ring like this, and I'll say that it's got, say, a radius r and charge. So we'll say it's got a net charge of q, and q could be positive or negative. Yeah, so here's our charge distribution, and now I'm going to wonder about, say, let's think a little bit conceptually. So let's wander a test charge around the ring. So I could imagine putting the test charge at lots of different places. So I'm going to do something though. I'm going to take this ring, and instead of imagining it being flat here, let me turn it on its side like this. So here is the center of the ring, and it's still got radius r, and this charge q is smeared along the edge of the ring. And let's think about stuff. So I could put, let me put the net charge, not the net charge, excuse me. Let me put the test charge, say, here. So if I put the test charge there, I wonder, is this little positive test charge, let's imagine the test charge is positively charged, is it attracted to the ring or is it repelled from the ring? So in order to know if the test charge is attracted or repelled, I have to think about what charge is the ring itself. And so let me start by thinking about the charge of the ring as being positive. So in that case, I should see that the test charge is repelled. This will be the force on the test charge by the ring. If I take this test charge and imagine it further away, I should expect to see that the force on the test charge is smaller. And if I bring the test charge up really close to the ring, I should see big force. And you can see that as I take the test charge further and further away, I should expect to see that the electric force on the test charge gets smaller and smaller and smaller. All right, that's pretty simple. So that's what it looks like. It's going to look exactly the same on the other side because of sort of the symmetry of the situation. So if I go to the opposite side and imagine a test charge being placed the same distance from the nearby edge as up above, I'll see the same amount of force. I should expect some symmetry. And if I also do it over here, let's imagine that I put the test charge here in the same plane as the ring, and I'll see a force. This is supposed to be drawn with some perspective. So this will be the force on the test charge by the ring, kind of out of the page this way. And so what I mean by that is, here is the ring. So here's the center of the ring. Here's the radius of the ring, call it capital R. And I am just checking at places around here. And I find that over here, it's a radial outward force that way. Up here, it's a radial outward force this way. And if I check further away, I expect it to be smaller.
I'm not sure how the force dies off, but if I go really, really far away, like way off in the distance, the truth is I should start to see that the force is dying off inverse square. And what's more is it should start to behave like if I go very, very far away so that R is very big compared to the size of the distribution, we should start to see the ring behave more like a point charge. Right? So this is kind of, so this is the far away expectation. All right, so let's imagine taking this ring and turning it on its side. So what I mean by that is I'm going to kind of take this extreme perspective of looking in directions perpendicular to the plane of the charge. So along the axis of symmetry and also off the axis of symmetry. So let me go on the next page. I'm doing a conceptual exploration. So here is this ring of charge, and I'm drawing it very flat because we are looking from the side. And here is this axis of symmetry that I mentioned before. And if I look at places along the axis, then what I'm going to get is something like this. So the upper half of the charged ring is in some way, it's kind of like a bunch of charge on the upper side of the axis, and it's going to repel the test charge, right? So the upper half repels the test charge, but in black, let me think about the charge on the lower half of the ring. It's also going to repel the test charge. And because the lower half of the ring is the same amount of charge, the same distribution of charge, and the same distance away from the test charge, the lower part of the ring is going to give me a force on the top side that has exactly the same magnitude as the force. So this is the force from the lower, and this is the force from the upper, right? And we should expect to see that the force from the lower half has the same magnitude as the force from the upper half. And this is a symmetry argument. It's the same amount of charge, the same distance away, in the same shape. Same amount of charge, same shape, oops, not share, but shape, and also the same distance away. So these three things lead to that equal sign. But they are different in an important respect. So I can say that their magnitudes are the same, but their directions are different. But what's interesting is because their magnitudes are the same and because of the symmetry of this circle, then whatever angle you see here is going to be the same as the angle that you see there, so that their components horizontally are going to add up, but their components vertically are going to cancel. So what we summarize at the summary that we just explored is along axis of symmetry, I hope you can see this, but the electric field, field of the ring only points along the axis. The off axis components will cancel because of symmetry arguments. All right. So, but what about off-axis? Or actually, sorry, that'll be confusing. But let's check. So here is the side view of our ring of charge. And let's look at putting the test charge here. So the test charge being up here, this is going to be slightly more difficult. The idea is we're kind of far from the upper edge and a little bit more far from the lower edge, but the charge is all sort of localized over here, and we're kind of far away. So I expect the electric field to be something like maybe this. So this is weak. It's kind of like a weak force on the test charge because the test charge is far away from the charged ring. If I bring in Q closer though, so let's imagine I bring in Q and say put it here. So this is an interesting spot. What I expect is it's actually quite close to the upper edge and sort of far away from all this charge down here, but down here is a lot of charge, and up here is only a little bit of charge. But the point is, I think that the answer ends up being it's a force towards the center. And the closer that the test charge is brought to this upper edge of the ring, the force is going to grow, I believe, stronger and stronger. But actually, I'm not sure about that. But if you put the charge on the opposite side, you should expect to see quite a large force. And the reason is because on the top side, all of the charge is pushing upwards on the test charge. But on the bottom side, some of the charge is actually pushing down, and that charge is close. And the rest of the charge is further away, but it is pushing upwards on the charge. So you can kind of see us playing this conceptual exploration game. So we have lots of places, P, to ask what is the electric field. So let's pick an easy one to start. The easy problem to solve, it turns out, is this. What is the electric field of the uniformly charged ring along the z-axis? This one turns out to be sort of the easiest one to solve. Let's set this up. So actually, you know what? I didn't identify that the z-axis, or what the z-axis has to do relative to how the charged ring is in the picture. So what I mean by it, so let me change this. So it's the ring, it's the electric field along the axis of symmetry. So this is the problem that I want to solve, the axis of symmetry. So Here's what that looks like. So here is the ring of charge, say from the side view. This is the center, and the axis of symmetry is this this line, and it actually continues onto the other side. So it's really through the center on either side of the ring. So let's identify this axis of symmetry as the z-axis. So I'm imagining putting the let's say the z-axis is up, the x-axis is sort of left and out of the page, the y-axis is towards the right and out of the page, and the ring, it sits in the xy plane. So this is xy, ring is in xy plane. And we'll say for simplicity, centered at the origin. I tend to use the symbol script O for the origin. Yeah, so let's also say, because we want to actually solve a problem, so let's put some variables in here. Charge, so this is the net charge of ring. We'll just give it symbol capital Q, and radius of ring, let's give it capital R. So the radius of the ring is capital R, and the charge Q is uniformly smeared. So uniform charge density. So let's start solving the problem. So remember that in these line charge problems, these line charge problems involve a linear charge density, and we're calling it lambda. And so in this case, lambda is the charge Q, not divided by R, but divided by the circumference, so 2 pi r, right? The charge is smeared over the circumference, over the edge of the ring. So it's Q over 2 pi r. So that's good. Earlier we used lambda dx to describe a small amount of charge, but we don't move necessarily along the x-axis or the y-axis alone to move along the ring. We have to move along the edge, and the edge, moving along the edge or moving along the circumference, is often described as ds. So ds is a small arc length. So we've got lambda is Q over 2 pi r, and a small amount of charge is going to be associated with a small arc length. So charge per length times a small arc length is a small amount of charge. So this is all so that I can do the following, right? The small contribution to the electric field at P is going to be 1 over 4 pi epsilon naught dq, the small amount of charge, an r hat, and an r squared. So I have started to fill in what I mean by dq. It's going to be lambda ds. I still need to do a little bit more work, honestly, on dq. I need to figure out how to write down r hat, and I need to figure out how to write down r squared. So I'm going to redraw the problem so that it looks a little bit cleaner. So this is the z-axis. I'm going to take this picture and imagine rotating it like this. So I'm going to imagine sweeping the x-axis all the way around until the x-axis is on top of where the y-axis used to be. And that drawing looks like the following. So here is the x-axis rotated around to where the y-axis used to be. And the y-axis would have rotated as well to here. So this is the y-axis. And if I redraw the ring of charge in here, here it is. I didn't really do a very good job, but it's supposed to be a circle of radius r centered at the origin there. So the little ds's, I want to study those a little bit. So I'm going to pick one. Let me pick this one. Here's a small arc length, and in this small arc length is a small amount of electric charge that's equal to the charge density times the length of that small arc length. That small arc length is spanned by an angle d phi, a small angle phi, but it's at the distance r. So r times a small angle is equal to a small arc length. And let me describe a side note. I know that the circumference is 2 pi r. And let me tell you why. Whoops, not why, but why is that true? So the idea is if I can integrate small arc lengths all the way around the ring, I should add up a totality of what is known as the circumference. So if I claim that small arc lengths are at the radius r sweep by a small angle d phi, then what I'm going to integrate or add up is small pieces that are r times d phi long. And in order to go all the way around the ring, I range with the variable phi all 360 degrees, but I have to use radians. So when you do this integral, it's r times phi evaluated at 0 and 2 pi. And when you finish the integral, it's just 2 pi r. Right? This is why the circumference is 2 pi r. It's because I can imagine adding up small arc lengths. So these arc lengths, r times d phi, these are the ds's. And that gives me a way to talk about the dq's, the small amounts of charge that are kind of associated with the sweep d phi at the radius r. So dE at P, this is the electric field, or the small contribution to the electric field at a place P, is going to be equal to, it's 1 over 4 pi epsilon naught, and now we can fill in a little bit more. The little bit more is, so dq is lambda ds, but ds is r d phi, so this is lambda r d phi. That's dq. So yeah, so then I need to still do this r hat over r squared business. So let's concentrate on r hat and r squared. So this angle phi is sort of strange. Let me show you how it gets measured. So do you remember that here is the x-axis, y-axis, and let's imagine something that you might have to review. It's called the unit circle. So a unit circle is a circle of radius 1, but the way you use this is you imagine going around the circle using angles. And so I'm going to call this angle phi. Sometimes it's called theta, but in this picture I'm going to call it phi. And the way phi is measured counterclockwise from positive x axis, right? That's the instruction on how to describe phi So you can see that, for example, if I go all the way over to here, so phi in this case is measured from the positive x-axis. This is a number in between pi over 2 and pi, right? It's a number between 90 and 180 in degree measurements. But this is how phi is measured. So I had to remind you of this because I want you to imagine this x-axis and this x-axis, they're the same, and the y-axis, they're the same. So in this picture there is an implied z-axis up out of the page. We are looking at electric field values, say, along the z-axis. So we'll put the place P up there, and we're going to use the angle measurement. This right here is how we're going to range over our charge distribution. This is the ranging variable, or the ranger variable, which is also known as the dummy variable. So here is a particular value of phi. There, and there is a small charge dq sitting there, right? This is the place P. Remember, we're going to look for only electric fields along the axis of symmetry, and as drawn, the axis of symmetry is the z-axis. So let's figure out what the r vector is associated with r hat and r squared. Remember that the r vector is the vector that points from the charge dq to the place P. The place P, I need to give it a coordinate. So since it's on the z-axis, the x and the y coordinates are 0. And it kind of looks like it's a height, sort of a distance away from the origin. Let's call it height h. Right? So this is the coordinate of the place P along the z-axis. So it points from dq to the place P. And I need to write this vector out. And in general, this vector is an x component plus a y component plus a z component. The z component is really easy. It's just the well, actually, yeah, it turns out it is easy, but let me get to that first. So let me redraw this a little bit better. So here is this circle. It's of radius r. This is the x direction and the y direction. And let's say that this is where the charge dq is. And the first thing I'm going to do is figure out this vector. So this is a sub-problem. How do I write down the vector v that points from the origin O to the charge dq, right? So that's how this is what I want to do. So the vector v that points from the origin points from here up to the location dq, where dq is a radius capital R away, but at an angle sweep of phi. And the answer looks like this. It's r cosine phi times I hat plus r sine phi times j hat. So the vector r is the vector that goes from dq to P, but I can build this vector the following way. It goes from dq to the origin, and then afterwards, once you get to the origin, you use a different vector to go from the origin to P. So if I want to go from dq to the origin, then what I want to do is I want to use v, but I want to use it backwards. So I'll use v to go backwards from dq to the origin by using it backwards, right? Negative v. And then I'll add on the vector that goes from the origin up to p. And that vector is h k hat. And so this r vector is simple. It just looks like minus r cosine phi I hat minus r sine phi j hat, right? That's what negative v is, and then I add on h k hat. So here is the r vector, and this is a useful result. It's going to be useful because I can get r squared, that is the distance squared, and I can get r hat. Both of those things come from the r vector, so I have to get the r vector first, right? Because I want r hat, I need to get r first, and if I want r squared, honestly, I need to get r first. So r hat, let's do r squared first. R squared is the vector r dotted with the vector r. That's how you get r squared. This is really just the Pythagorean theorem as well. So regardless of whether or not you use Pythagorean theorem in 3D or r dot r in 3D, the result is when you are looking at the vector r that we just wrote down, what happens is you get r squared cosine squared phi plus r squared sine squared phi plus h squared. And you notice that in this distance squared, which is the result of a dot product, there are no vectors left. It's purely a scalar, right? There's no I hat, j hat, k hat left over. They all dotted away. So that's what's left over. And what this means is that I can also write down r hat. R hat is the r vector divided by r squared. And actually, I'm forgetting, if you look at these two terms, you can use a trig identity to rewrite this as just r squared plus h squared. So everything that I put this bracket around simplifies to capital R squared. So actually, it's not r squared on the bottom. So the unit vector is the r vector divided by the length r. So it's actually the vector's magnitude, not the magnitude squared. This right here is the magnitude squared. And what goes here is not the magnitude squared, just the magnitude of the first power. So if you just fill in, this is minus r cosine phi I hat minus r sine phi j hat plus h k hat, and then you divide by the length of r, and the length of r is the square root of the length squared, so it's r squared plus h squared to the 1/2 power. So all this means that I can write that the electric field at P has a contribution, this infinitesimal sense, of 1 over 4 pi epsilon 0. It's got this lambda r d phi. I can divide by r squared, so that's r squared plus h squared, quantity. And then I multiply by r hat. So r hat I wrote there, so it's, I'll put it in brackets. It's minus r cosine phi I hat. You notice it is a vector, so it's got all the unit vectors. So minus r sine phi j hat plus h k hat. And then I divide by r squared plus h squared to the square root. There's a little bit of simplification we can do. We can take this thing and this thing, which look really similar, and put them together. So I'll go ahead and do that. But I'm going to sort of also make some small changes. So there is lambda r over 4 pi epsilon 0 r squared plus h squared raised to the 3/2 power. I've got power of 1 and a power of 1/2, and 1 plus a half is 3/2. And then I've got d phi. That's a factor. It's just a small radian angle, right? An infinitesimal radian angle, but it is a factor. So it's it's multiplying with the minus r cosine phi I hat minus r sine phi j hat plus h k hat, like this. And so you'll notice that this and this are the two factors, and the second factor is phi dependent, and this is phi independent. And so nothing about capital R. Capital R is just the size of the ring. Nothing about H has anything to do with phi. H and phi are independent directions, in a sense. H is purely a z direction thing, and phi is purely an x and y combination thing. Lambda, it's uniform, so uniform means there is no phi dependence. Yeah, so this is all phi independent, and this is all phi dependent, actually, except for that. That's not phi dependent, but I'm going to leave it over here because it's sort of a directional thing. And so now I can write that the electric field at P due to the ring is equal to the integral of all the small pieces of electric field at P due to small charges on the ring, right? So I'm going to add up ranging over the ring, and these are all small vectors, actually. Sorry about the light. So when I do this integral, when I go around the ring, I have this prefactor that's all independent of the ranging variable, so it can all come out. And that's all sits in front, and I do the integral, and I range over the entire ring with the ranging variable d phi, and I do pieces in the x direction, the y direction, and the z direction. Right, so this has become my problem. Okay, and so, for example, the x component of the electric field, so the electric field is a vector, but I'm going to describe only the x component. The x component is the thing that has an I hat on it. And can you see that this is the sum of three terms with a common factor? So this is going to multiply this, as well as this multiplying that, as well as this multiplying that, and then you're going to add all three things together. But even after doing the integral and adding things together, you're still going to be separate in direction. So anything to do with I hat is never going to turn into something that looks like j hat. So the x direction just keeps to itself. And what this amounts to is the following. So E sub x, the x component of the electric field, at P due to the ring, net, so it's the net electric field in the x direction, is going to be lambda r over 4 pi epsilon 0 r squared plus h squared raised to the 3/2 power times the integral from 0 to 2 pi d phi of minus r cosine phi I hat. And if you do a little bit of work, you'll notice that this and this, they are constants of the integration. Capital R is independent of phi, so capital R, it's easy to see, can come out front and the minus sign can come out front as well. But it turns out that the I hat can also come out front because I hat is independent of angle. I hat strictly only ever points in the positive x direction no matter where you ask, no matter what angle you ask at. So I hat is constant as far as the integral goes. And so if r and I hat and the minus sign can all come out front, they can join the lambda r. So it goes minus lambda r squared I hat, and then divided by 4 pi epsilon 0 r squared plus h squared 3/2 power. But then I'm left over with the integral from 0 to 2 pi of the cosine of phi d phi. And it turns out that this integral is 0. The integral of cosine goes up to sine, and the sine evaluated at 2 pi and at 0 both happen to be 0. So this turns out to be 0. So there is no x component to the electric field. If I go back and, similarly, you can guess that the y component is 0 as well. So the y component will be 0, and you can go up and do the integral if you want. You'll do the integral of sine of phi from 0 to 2 pi, which becomes negative cosine, and negative cosine at 2 pi has the same value as negative cosine at 0. So when they subtract, they just subtract each other to 0. So that's what will happen in the y direction. But E sub z is equal to lambda r over 4 pi epsilon 0 r squared plus h squared raised to the 3/2 power. So that's all denominator stuff. And looking at the expression, and we're looking at the z component. The z component is the k hat thing. So you have h and k hat. These are constants with respect to changing angle phi. So the z direction doesn't care what angle you ask. The z direction is always the same. It's always up away from the xy plane. And then h is independent of the angle phi. H is just some distance of the z axis. Doesn't depend on what angle you put dq at. So h and k hat are actually constants. So I'm going to pull them out of the integral, and the integral left over is 0 to 2 pi d phi. So this is the z component. Oh, you know what? I'm so sorry. I actually kind of made a mistake. The mistake is remedied. I'm going to remedy this really quickly. The x component of the electric field times I hat is all this stuff that ends up being 0. And the y component of the electric field is a bunch of stuff that becomes 0. So some of you know what I just did. Others are like, what the hell did you just do? Think about it a little bit. Mostly, every time I claim an equal sign, if I'm claiming that something that obviously is a vector is equal to something that's a scalar, I've done something wrong, because vectors are never scalars. So explicitly, I have a vector on the right-hand side, albeit, it turns into 0, but it was a vector, and this vector can't be a scalar. So when I was missing the I hat, it wasn't a good equal sign. It was a bad equal sign, actually. But if I plug in the I hat on this side, this is the x part. This is the x direction part of the full electric field vector. Okay, so here I've done it again. So I'm going to tack on the k hat. This is the z component of the electric field vector, or it's the z part of the vector. So the full vector looks like this. This is the electric field at P. It's equal to the x component times I hat plus the y component times j hat plus the z component times k hat, because the z component it doesn't include the vectorness. It just tells you how big it is or how much it is in the z direction. So anyways, but it's all fixed now. This looks good. The integral, this kind of thing, is very simple. It just turns into 2 pi, and we get that the z component of the electric field looks like lambda r h times 2 pi. That's the result of the integral, and I'm dropping the k hat because I'm not including it on the left side. And then the denominator is like this. And you might be tempted to take this 2 pi and 4 pi and divide them partially, and you get left over with a 2 on the bottom still. But I'm not going to do that. I'm going to rewrite this and just write that the net electric field at P due to ring of charge is Z component only, and it looks like this. It's 2 pi r lambda, I'm going to put them all in parentheses, multiplying h divided by 4 pi epsilon naught r squared plus h squared 3/2 power times k hat. So I'm claiming a vector equals this vector, and it's purely in the z direction. Okay, so let's test our answer, right, to see if it makes sense. So here is our problem, but I'm going to turn it sideways. So here is the z-axis, and that direction is the negative z-axis. That's the negative z direction. So what if h equals to 0? If h equals to 0, this means I'm asking what is the electric field in the dead center of the conducting ring. So I expect, what do I even expect? I expect actually that the electric field goes to 0 at this place P, right there. And the reason I expect it is if you look at charge here versus charge here, the charge here if the ring is positive, it will repel a positive test charge, and this charge will repel it backwards. Can you see that? So the charge on opposite sides of the ring, because they're the same at the same distance, right, because of the symmetry is going to be that this charge is repelled in all directions in the xy plane equivalently. So just by symmetry. This is what we expect. So let's test our answer. Here's our answer. This is the answer here. And let's put in h equals to 0. So if you put in h equals to 0, on the top I get a 0. That's a good sign. And on the bottom there's an h, right, that goes to 0. And you don't want 0 over 0, but that's not what we have. We actually have 0 over something that's not 0, because capital R, presumably, right, this charge is distributed on a ring of non-zero radius. So the test is a check mark, right? It does go to 0 at the center, and that's what we expected. What if we go far away? Far away means that we go far enough away with h such that, in a sense, it's way bigger than the size of the distribution here. So far away, right? Far away means the following thing. It's kind of take the limit as h goes to, say, infinity, right? And we'll keep r finite. R is finite, but h goes to infinity. and we are checking what happens to the electric field at the place P if the place P is infinitely far away and the radius of the circle is some finite number. So if you do this, this kind of a check is sort of hard, but essentially what we're doing is we're taking the limit as h goes to infinity, but r is finite, of this expression here. So we want to take that limit of 2 pi r lambda h divided by 4 pi epsilon naught r squared plus h squared 3/2. And there's a bunch of stuff in this expression that has nothing to do with this limit. The r, the lambda, the 2 pi, the 4 pi epsilon naught, and the r squared, none of that, well actually I can't quite deal with the r squared quite yet, but so this is equal to 2 pi r lambda divided by 4 pi epsilon naught, and then the limit as h goes to infinity of h divided by r squared plus h squared to the 3/2 power, right? So if I look at this expression, I hope you can see that what I'm going to get is 2 pi r lambda over 4 pi epsilon naught. And in this limit, check this out, if h is huge and then I square it, compared to a normal-sized r, some finite value of r squared, h squared just swamps r squared. So this expression here turns into h over h squared to the 3/2. And if you do a little bit of math, right, we're taking h squared, you take the square root, and then you cube it. And what you get from that is 1 over h squared. So let me show you why this is interesting. I just showed you that the electric field at P for h going off to infinity, right? So this is very far away. Looks like 2 pi r lambda, let me put that in parentheses, divided by 4 pi epsilon naught, 1 over h squared. Let me remind you of what 2 pi r lambda is. Remember that lambda is the charge per 2 pi r, right? This is the charge on the circle, and then we divide by the circumference. So the circumference times lambda, here's the circumference times lambda, that's just the charge of the ring. So it looks like q over 4 pi epsilon naught, 1 over h squared. This is the electric field of a point charge at the distance h from the point charge. That is, if we go really far away, this ring behaves as a point charge, so far away. This kind of a test, check. Right? If we go far enough away, then we can't tell the detail, the fact that this is a little ring. If you go far enough away, this just looks smaller and smaller and smaller and smaller, more and more like a point the further away you get. So we just checked this. That's another test. Yeah, there's some other tests you can do, but that this is how we gain some confidence that the answer we have seems like a good answer. And now you can go and compare with somebody else, and maybe you made a small error and you're missing a factor of 2, or you did an integral wrong and somebody's like, no, those integrals in the x and y directions, they are 0, when you may have made a mistake or something. But I hope you can, I hope you got something from this lecture. It's just probably seems like a bunch of math. Yes.